Hello and welcome to the closed loop control series. In this episode, we will be covering the basics of terminology and definitions, as well as bang-bang control, the simplest form of closed loop control. Let's get started. Control is defined as driving a process towards a desired set point. The process is the output variable we want from the system, in this case, the motor speed, while the response is the input to the system that changes the process output, in this case, the motor driving voltage. The set point is the desired value of the process variable. This can be a constant or a function of many other variables. The error is the difference between the set point and the process variable. Mathematically, the error is equal to the set point minus the process. An open loop controller uses predetermined response values to achieve the desired process set point. They're good for low precision or disturbance shielded high precision systems. Closed loop controllers used feedback from process sensors and, optionally, predetermined response values as well to achieve the desired process set point. They are good for systems that must tolerate disturbances of any kind. Many processes simply do not need closed loop control, such as industrial pumps or fans. It doesn't matter exactly how fast they spin, just that they do. Other processes are so dynamic that they can only be properly characterized through trial and error. One good example is the Space Shuttle main engine startup sequence, which had to run open loop to prevent catastrophic failure due to transient conditions that no closed-loop controller could predict and handle safely. However, during steady-state operation, the Space Shuttle main engines run on a closed loop. This regime is much simpler because there are no transient conditions, and only relatively fine adjustment is required to achieve the desired performance. See Scott Manley or Everyday Astronauts videos about the Space Shuttle main engine for more information. Closed-loop control is required when the process variable is depended upon by another layer of control. For example, when your DC motor velocity control is used with a motion profiler to achieve precise position control. I'll cover this more in a future episode. Brushed DC motors produce torque proportional to the effective voltage across their rotor coils, which is analogous to the difference between how fast the motor wants to spin at that voltage and how fast it is actually spinning right now. When full voltage is applied at rest, a large torque is produced. When full voltage is applied at full speed, almost no torque is produced. When full negative voltage is applied at full positive speed, a very large negative torque is produced. And when a small positive voltage is applied at full positive speed, a moderate negative torque is produced, slowing the motor down. Watch ElectroBOOM's video for a more in-depth explanation of this. He has some really good visuals and explanation that I don't think I can improve on, so I'll leave a link down in the description. So for the simulation model, I will use the torque-speed relationships from VEX Pro, a friction force that I got from a help page on the MATLAB documentation, and a moment of inertia that I will define arbitrarily to form a simulation of our DC motor spinning a flywheel. This is programmed in Python using browser-embedded vPython at glowscript.org. I will link the simulation in the description so you guys can play around with it. The inputs to the simulation are hard-coded and the outputs are produced in interactive graphs. The physics simulation runs at 1 kHz, but controller periods can be any whole number of milliseconds, so you can see how the controller frequency and period affects the quality of the control system. So let's look at some sample output. On the left we have speed versus time, and on the right voltage versus time. The graph shows the typical operation of a DC motor when given a constant driving voltage. The speed increases very sharply initially and then flattens out as the motor reaches the speed that it wants to spin at that particular voltage, minus some speed due to friction. Bang-bang control is the simplest form of closed-loop control. It produces a 100% positive response when the process is less than the set point, and a 100% negative response when the process is greater than the set point. Here's a simple bang-bang controller. The set point is 3,500 RPM. In the speed graph, we clearly see a quick rise followed by oscillation. On the voltage graph, we can see that the voltage is always either plus 12 or minus 12 volts. An important thing to note with bang-bang controllers is that you need to use the full range of the motor in order to be able to use the full range of the output. The response variable has to be the maximum possible that your system can provide. Otherwise, you can't use the full range of it, which is fine for a set point like this, which is in the middle of the range, but if you try to change the set point, you're going to have problems. Also, note that the oscillation is biased down somewhat. This is due to both friction and the DC motor mechanics. As I mentioned earlier, when it drops to minus 12 volts, that's producing a lot more negative torque than the motor produces by the plus 12 volts, just because of the difference in speed from where the motor is spinning to where it wants to be. Increasing control frequency will decrease the oscillation amplitude linearly, which improves precision and safety. However, extremely high control frequencies, in excess of 1 kHz, are often impractical to implement due to hardware constraints. A low control frequency is critical when only one central computer is available to process all inputs and outputs in a complex system and run multiple control loops simultaneously. This can reduce cost and complexity of the overall system and is often applicable to hobby robotics. Here we have 3 different control frequencies so you can see the difference in the oscillation around the set point. At higher frequencies on the left, the oscillation is quite small, whereas on the right, as the frequency of the controller drops lower, so does the frequency of the oscillation around the set point, and as such, the amplitude increases drastically. Furthermore, when we go to an extremely high frequency of 500 Hz, you can barely see the oscillation in the zoomed out view. When we zoom in, you can see an oscillation amplitude of about 35 RPM peak to peak. This is very good precision, which is always afforded by an extremely high control frequency. However, in practice, you can usually only achieve this high of a control frequency with a dedicated controller that only runs a single motor. The other factor which affects the oscillation amplitude is the maximum acceleration of the system. For a rotational system like this, the acceleration is the net torque divided by the moment of inertia. The acceleration multiplied by the controller period is the velocity error that will be produced every controller frame by a bang-bang controller. PIDF controllers are desirable because they can reduce the velocity error without increasing controller frequency or changing system dynamics. So here you can see the effects of varying the moment of inertia. On the left, we have a 5 times lower moment of inertia. On the far right, we have 5 times the moment of inertia. The inverse of that is the acceleration. So on the right, you can see a very, very small oscillation, which is similar to the effect from increasing the control frequency a lot. And on the left, you can see a huge oscillation, which is similar to the effect of decreasing the control frequency a lot. Thank you for watching. There will be more videos in this series covering a lot more things. The next episode will be on PIDF control, as I mentioned in the previous slide. Please let me know if I'm wrong. I'm very new to this, but please post any constructive criticisms you have down in the comment section. I'll be sure to try to post some corrections for them. But thank you so much for watching, and have a nice day. Please come back. I'm really trying my best here.